So next, we are going to switch gears and talk about generators of transformations. So I'm just going to introduce this idea, and later we'll come across this many times, so it'll be finessed. So in quantum mechanics, the state of a system is described by some wave function on some Hilbert space. So we have some wave function, and it's some member of some Hilbert space. Now, suppose we take our system and do some transformation, and that transformation could be that we could say rotate the system. We could say translate it. We can translate it in time or space, etc. Now the question is, what is the transformation that can result on psi as a result of the underlying transformation on the system? So to answer this, the answer to this fact is a very central fact of quantum mechanics. So suppose that psi is a state of some system, and we make some changes to the system, which is parameterized by some real parameter A. So this real parameter can be, for example, a rotation. It can be a translation in time. It can be a translation in space. Then, so psi naught is our initial state of the system. Then the state of the system after the transformation, which is denoted by, say, A, so psi A will be given by some unitary operator which depends on A acting on psi 0. So this is a very general result. So U is a unitary operator. That means that U dagger is equal to U inverse. Now, because U is unitary, we can write U in this form where e to the power minus a IAT. And then if U is unitary, that means that T is Hermitian. And then T is known as the generator of the transformation. So a good rule of thumb to find T is that T is the quantity that is conserved if the corresponding transformation of the system is a symmetry. Let's take rotational invariance. We know that when we have a system which has rotational invariance, its angular momentum is conserved. So in that case, if the rotational invariance is around the z-axis, T is going to be given by J of Z. So even if the system is not invariant under rotation around the z-axis, the transformation that rotates the Hilbert space around the transformation that results on the Hilbert space as a result of the rotation of the state around the z-axis will still be given by Jz. So similarly, if we are talking about, say, translation in time, then T will be given by the Hamiltonian. And of course, this is related to the fact that the energy of a system is conserved if the system is time invariant. Again, translation in space, T will be given by the momentum operator. And lastly, of course, well, rotation is t will be given by the angular momentum operator S or L. So let's look at this in more detail. So our first example, we already know this, that if I have a wave function at time t, it's given by the time evolution operator, which is e to the power minus I by h bar h of t psi acting on 0. And this is exactly the form. This is a unitary operator, and h is a Hermitian operator. This is unitary, h is Hermitian. And if I have the translation of a wave function, then that's given by a momentum operator. And this is easy to show. All we have to do is to expand the left-hand side in a Taylor series and use the fact that the momentum operator in the position representation is given by h bar by I d by dx. And you can show very easily that this is up to order A, you can show that this is correct. And the last example we're going to do is the rotation of a spin half particle. So it's a spin half particle. And we are going to do a rotation of this particle around the z-axis. So we know that the SZ operator is a 2 by 2 matrix, and therefore the wave function is going to be given by a matrix wave function. So this is our wave function. Now, if I rotate this, so I get rotated by, say, some angle theta, then I'm going to have e to the power I or minus I theta times sz. So what acting on psi 0? What is this thing? This is nothing but e to the power minus I theta by 2. This is 0, 0, e to the power plus I theta by 2 acting on psi 0. So psi of theta is then going to be given by e to the power minus I theta by 2 psi 1 e to the power plus I theta by 2 psi 2. So an interesting consequence of this is that if I rotate it by 360 degrees, that is, I take theta to be 2 pi, because of the fact that the eigenvalues of Sz are half and minus half, which is due to the fact that we have a spin half particle, that psi of theta rotated by 2 pi is going to be minus of psi 0. So as we take a particle which has, say, spin half, and we rotate it by 360 degrees, the wave function goes to minus itself. And this is very, very characteristic of a half integer spin particle.